Hello and welcome to this lecture of algorithms. And today we'll be looking at the method of solving recurrences, that is your master method. So far we have seen your substitution method, then we saw your recursion tree method, after that we saw your iteration method. And we solved many recurrences of two types mainly. One was your decreasing function and the other one was your dividing functions. Today we'll be looking at the fourth and last method of solving your recurrences, and that is your master method. So it is also known as Master's theorem. What you have to do here is that we don't actually solve the recurrence. What we do is that we have to memorize certain cases, and once we memorize those cases, we can quickly say what will be the time complexity of a recurrence, okay, just by looking at it. So initially it might be a little difficult to comprehend or to memorize those cases, but once you get a hang of it, it will be pretty easy to solve these recurrences, okay. So when it comes to competitive exams or quickly deciding over the time complexities of algorithms, you don't have time there to use substitution method or to use iteration method. What you do is that if you memorize this or if you have good hold over Master's theorem, what you can do is that you can quickly say what the running time complexity of that algorithm will be. So as we have seen in previous lectures, that we first saw how we can solve recurrences which were of the type which were of decreasing type, and then we saw those recurrences which were of the type that is of dividing functions. So there were basically two reasons why we saw those two separate classes. One was obviously for better understanding, because once you separate decreasing functions from dividing functions, you get a little bit clear picture and you understand how we solve them. The second one is that we will see Master's method for these two classes differently. Okay, we'll first see the Master's theorem or Master's method for your decreasing functions, and then we will see your Master's method for your dividing functions. So that was also one of the reasons why we broke down the previous topics, the previous methods into two classes. Okay, so we will begin with your decreasing functions. Fine. So I will write here a general form of your decreasing function. Okay. So if we have t of n which is equal to a times t n minus b plus f of n. Okay, so this is a general form of your decreasing function. We have seen many decreasing functions that were of the type say t n minus 1 plus 1 or t n minus 2 plus n, or we had 2t n minus 1 plus n or plus 1. So this is a general form. You can substitute value here and you can get different answers. So here the condition is that your a should be greater than or equal to 1. Obviously it can't be 0, but because then this whole term will become 0. And your n should be greater than 0, anything greater than 0. If you take any value greater than 0, that will decrease the value of n with some value, and you can have a stopping condition, or means you can solve it recursively. And also your f of n is order of n raised power k. Okay, where k is greater than or equal to 0. So what does this do? Okay, so this is the first one, that is your this is decreasing function. So what does this decreasing functions actually do? They take your problem of size n and they break it into small subproblem of size n minus b. Okay, and then they go on recursively solving it. So here we assume that your f of n is asymptotically positive. Okay, so what do you mean by asymptotically positive? Means that your f of n will always be positive for sufficiently large values of n. Fine. So here a, like I said, will be greater than or equal to 1 because it can't be 0. Your n, sorry, here it is b, it's not n. So your b should be greater than 0. okay, then only it will be decreasing, and f of n we assume that it is of the order n raised power k, fine. So we have two cases here. So we have case 1. So we have to only look at your A, okay. So if your A is equal to 1, whenever your A is equal to 1, your Tn will be equal to order of n into f of n, fine. And case 2 is that if A is greater than 1, then your T of n is equal to, it is order of A raised power n by b multiplied by f of n, fine. We also have a third case here, but we don't use that much, but I'll still write it here. That is, if your A is less than 1. That's not a very common case, so anyways we'll just write it down here. Then what will happen? Your T of n will be simply order of f of n, fine. So we have your decreasing function. This is your decreasing function T of n, which is equal to A T n minus b plus f of n, where we say that f of n is order of n raised power k, and we only take A, we only consider A when it comes to decreasing function. If A is equal to 1, we simply multiply n with whatever f of n is. If A is greater than 1, we take this coefficient A and we raised power n divided by b and multiplied by f of n, okay. So you can see in all three cases this f of n is important. Whatever f of n will be there, it will be. What differs is the coefficient. Here coefficient will be n, here coefficient will be A raised power n by b, and here coefficient will be 1, fine. So we'll take some examples, and that will that will explain what these cases actually mean. So let me take first example. If your T of n is equal to T of n minus 1 plus 1, fine. So here A is equal to 1, okay, and your B is also equal to 1, fine. This, it is 1 T n minus 1, B is 1, and your f of n is also equal to 1, fine. So when A is 1, which case is it? It is first case. So what will be T of n equal to? T of n will be simply equal to order of n multiplied by whatever your f of n is. What is f of n? F of n is 1. So it is order of n. So we have solved actually this recurrence using iteration method. We have solved this recurrence using your recursion tree, and we got there that it's order of n. So see now how easy it is. You don't even need to write this here, A is equal to this or B is equal to this. Once you get a hang of it, you can do this in your head. You can see that, okay, here A is 1 and your f of n is also 1. That means it will simply be equal to n, fine. So let's take another example. So if I have T n minus 1 plus n, okay. So here again A is equal to 1, fine, and your f of n is equal to n, fine. When A is equal to 1, we have to only look at this thing. When A is equal to 1, it is your case 1. So your T of n will be equal to order of n multiplied by f of n, fine, and f of n is n. So it will be order of n multiplied by n, and which will be equal to order of n square. Fine. So we don't even need to solve this. You can directly see that a is 1, f of n is n, and multiplied by n is n square. Okay. So I'm just writing here to explain it to you. Fine. Again, we'll see another example. T n minus 1 plus log n. Fine. We'll do it quickly. A equal to 1. Fine. And f of n is equal to log of n. So a equal to 1, it is the first case, means t of n will be of the order of n multiplied by log n. That is your f of n, which means that it is of the order n log n. Fine. So now we'll see a couple of examples for your case 2. So now for case 2, we have 2t n minus 1 plus 1. Now because we are having here a coefficient 2, so means here we have a equal to 2. Okay. So once a is greater than 1, that is, it is 2. So that means it is case 2. So what will be t of n equal to? T of n will be equal to, here b is 1 and f of n is also 1. Fine. So a of t of n will be equal to order of a raised power n by b. So what is a? A is 2. 2 raised power n by b. What is n? N is here n and b is 1. Okay. And what is your f of n? Your f of n is 1. So multiply it by 1. Fine. So what does it give us? It gives us simply that your t of n is order of 2 raised power n. Fine. So we don't have to solve it. We just have to see the coefficient. If it is greater than 1, we have to take this case. We have to take this coefficient raised power n divided by b. Whatever is here, this is n and divided by b. Okay. So another example we'll take 3t n minus 1 plus 1. It is almost the same example as the previous one. The only difference is here the coefficient is 3. So a is equal to 3, b is equal to 1 and f of n is equal to 1. Now a is 3 means a is greater than 1. It satisfies which case? 2. So t of n will simply be of the order a raised power, a is 3 raised power n by b. N is 1 and b is, n is n and b is 1. Okay. Then multiplied by f of n. What is f of n? F of n is 1. So it will be order of 3 raised power n. We'll take the last example for these decreasing functions. Say we are having 2t n minus 1 plus n. Okay, pretty basic example. So here we have a is equal to 2, b is equal to 1 and f of n is equal to n. Fine. So because a is greater than 1, that is case 2, so t of n will be equal to order of a raised power, a is 2 raised power n by b, n is n and b is 1, multiplied by f of n, and f of n is n. Okay. So it will be equal to order of n 2 raised power n. Fine. So we have seen Master's theorem and we have seen the Master's theorem for decreasing function, wherein we saw the basic template of the decreasing function, that Tn is equal to at n minus b plus f of n. And then we saw two cases, when a is equal to 1 and the other case was when a is greater than 1. We simply used it here. In the first case, we took n and multiplied by f of n, whatever was here. And in the second case, we took the coefficient raised power n divided by this b and multiplied by f of n. The third case is when a is less than 1 at that time means it will be negative. What you have to do is that you have to simply take this, whatever is your f of n, that will be your order of n. So again, we will first write the generic or the general form of your dividing functions. So we show it like this. Your t of n is equal to a times t n divided by b plus f of n. Okay? It is the same as we had for the decreasing function. The only difference is that here we have n divided by b, and in the previous case we had n minus b. So the conditions are there that your a should be greater than or equal to 1. Okay? Now in previous case your b was greater than 0 because we had to subtract. But here we cannot say that b is greater than 0 because 1 is greater than 0 and n divided by 1 is n. So that time it won't be decreasing function. So here we will be taking your b is greater than 1. Fine. And here your f of n is a little tricky, okay, rather than in previous case. So here we say your f of n is equal to n raised power k log n raised power p. Okay? So first of all, let us try to comprehend what this means. Okay? So what it means is that we are having a problem of size n. So what we do in dividing functions is that we divide this problem of size n into sub-problems, each of size n by b, and we solve them recursively till we get the result. Now one thing is there that maybe n by b is not an integer value, maybe it's a fractional value. In that case we have to take the floor value or the ceiling value. But if we take floor or ceiling value, that will not affect the overall asymptotic behavior. So we are only taking n by d, we are n by b. We are not concerned, we are not specifically writing floor or ceil because that won't affect the asymptotic behavior of this function. Again, f of n should be asymptotically positive, means f of n should be positive for sufficiently large values of n. Here a is greater than or equal to 1, b is greater than 1, I have said that, and f is equal to theta of nk log raised power pn. Now here the best thing about dividing functions or the Master's theorem for dividing functions is that we get a tight bound. As of now we have been solving your recurrences using your substitution method or using your iteration method or recursion tree method, and at the end we used to calculate the big O. Okay? So even for decreasing function we got the time complexity in terms of the upper bound, that is big O. But the best thing about Master's theorem or Master's method for dividing function is that you get the tight bound. Okay? So when you have your dividing function of this form, so what can be the possible cases here? Okay? So in order to focus on the cases, you have to remember this template of course, but you have to only, like in previous case, we had to only look upon a, that when a was equal to 1, okay, less than 1 or greater than 1, then we have to only focus on a. But here what we have to do is that we have to consider two things. The first thing is your log of a to the base b. We have to find log a to the base b. And the second thing that you have to see is k. Okay? That is this k, n raised power k. So these are the only two things that you have to focus on, you have to calculate initially. And depending on these two things, we can generate different cases. Okay? So I'll write down the cases over here. Okay? So we are having case 1. If log of a to the base b is equal to k, sorry, we have to, first one is greater than. So if log a to the base b is greater than k, then your T of n is theta n raised to power log a to the base b. So first case is pretty simple. Whenever you are this term, that is log a to the base b, it is greater than k, here, this one, this k, n raised to power k. What will be the order of T of n? It will simply be n raised to power this term, that is log a to the base b. Fine. Now your case 2. Your case 2 is when your log a to the base b will be equal to k. So if log of a to the base b is equal to k. But there are sub cases in this case, okay? When it is equal to k, we have to also see another thing. And first this condition is true that it is equal to k, and the second condition is, I will write it as 2.1. Okay, 2.1 is if your p is greater than -1. Fine. If your p is greater than -1, then it is of the order theta n raised power k log p plus 1 n. Fine. Another case is here 2.2, that is if p equal to -1. If p is equal to -1, then what will be your T of n? It will be of the order theta n raised power k log n. Fine. The last case here is 2.3, that is if p is less than -1. Okay. If p is less than -1, then it is simply theta n raised power k. Fine. And finally is your case 3. What will happen in case 3? In case 3, your log a to the base b will be less than k. So if log a to the base b is less than k, what will happen? Again, we are having here two subconditions. And what are the subconditions? The first condition is if p is greater than 0. Okay? If your p is greater than 0, then it will be of the order theta n raised power k log of n to the power p. Fine. And the last case is 3.2, that is the sub case of this, that if p is less than or equal to 0. Okay? If p is less than or equal to 0, it will be of the order n raised power k. Theta n raised power k. So these are the three cases. In each case, we have to check these two values, log a to the base b and k. So initially you will get which case it is depending on the value of log a to the base b. If it is greater than k, it is case 1. If it is equal to k, it is case 2. And if it is less than k, then it is case 3. For case 1, there is no headache. You simply take it. Then if it is greater than k, you simply take T of n is equal to log n raised to power log a to the base b. But the sub cases arise in case 2 and case 3. Means in case 2, when log a to the base b is equal to k, you have to also check p, this p, log p raised to power n. If p is greater than -1, then you have this. This will be the tide bound for your recurrence. If p is equal to -1, then it will be theta n raised to power k log of log n. If p is less than -1, it will be theta of n raised power k. And same goes for case 3. But here we have only 2 cases, we don't have 3 cases. Means we have only greater than 0, and for less than or equal to 0, we have combined them. Okay. So now we will take examples and we'll see how we can use Master's theorem for your dividing functions. So first example we'll be taking is a pretty simple example. Tn is equal to 2t n by 2 plus 1. Okay, this is a simple example. So here, one thing that comes to mind when you see Master's theorem for dividing functions is this theta of n raised power k log raised power pn. You might be thinking that it's not necessary that every time we'll be having a log in our recurrence. So what happens at that time? So what you can do is that at that time you can keep p as 0. So what will happen? Anything raised power 0 is 1. So that term will vanish. So you can use log raised power 0 n, okay, in order to match it with that. So if we look at this and compare it with that, here we are having a is equal to 2, b is also equal to 2, fine. Now f of n is little tricky. What we'll do is that f of n, we can say it is equal to n raised power 0 log of n raised power 0. Can't we say that? It will be 1, that is 1. And it will imply that your k is also equal to 0 and p is also equal to 0, fine. Now what we will do, we have to calculate this term first, log a to the base b. So your log a, that is 2, to the base b, that is 2, it is equal to 1. Log 2 to the base 2 is 1. Now we will compare it with what? We will compare it with k. So k is 0 and log 2 to the base 2 is 1, means it is greater than k. Which condition does it meet? It meets first condition, that your log a to the base b is greater than k. K is your 0 here and 1 is greater than k. So we can simply write your t of n is theta n raised power log a to the base b. Log a to the base b we have calculated, it is 1. So your Tn is of the order theta n. We will take another example. T of n is equal to 2t n by 2 plus n divided by log n. Okay. So we'll solve it a little. It will be equal to 2t n by 2 plus n multiplied by, if I take this log up, it will be log raised power minus 1 n. Fine. So now we can calculate, or we can say about those terms. Here a is equal to 2, fine. B is equal to 2, fine. And f of n is n raised power 1 log raised power minus 1 n. So means n raised power 1 means your k is 1 and log raised power minus 1 means p is equal to minus 1. Fine. Now first we have to calculate this log a to the base b. So log a, that is 2, to the base b, that is 2, that is equal to 1, just like in previous example. But here k is equal to 1. So what does it mean? It means that it is equal to k, which is also equal to 1. Fine. So now log a to the base b is equal to k, which condition meets? Your second case meets. But here we have to explore further. Now we have to check the value of p. So what is p equal to? P is equal to minus 1. P is equal to minus 1. So which case it meets? 2.2. So case 2.2, p is equal to minus 1. Means t of n will simply be equal to theta of n raised power k log of log n. Fine. So we have to only substitute value of k, that is 1. So it will be equal to theta of n log of log n. So this will be the time complexity of this algorithm. 2t n by 2 plus n by log square n. Fine. This is almost same as previous example. The only difference is here we are having log square. There it was only log n. So if we check here, a is equal to 2, b is equal to 2, okay, and f of n is equal to n multiplied by log raised power minus 2n. It will imply your k is equal to 1 and your p is equal to minus 2. Okay. Again, we'll calculate log a to the base b, that is log 2 to the base 2, that is 1. 1 is equal to k, because k is also equal to 1. So again it meets k is 2. Now we will look at the value of p. So value of p is minus 2. Okay. So what is minus 2? Your minus 2 will be, minus 2 is less than minus 1. Okay. So implies case 3. So case 3.3, this one. Sorry, it's 2.3. Means p is less than minus 1. So it will simply be of the order n raised power k. So it will be of the order, k is your 1, it is of the order n. Moving on, we'll see a couple of more examples that will, we'll try to see if we can solve it using case 3, and that will finish it. So if we see t of n is equal to 2t n by 2 plus n square log n. We can have a recurrence of this type. So here a is equal to 2, b is equal to 2, fine. Your f of n is n square log n, means the n raised power 2, means k is equal to 2 and p is equal to 1. Fine. Now let me take log a to the base b. Fine. So it is log 2 to the base 2, that is equal to 1. But 1 is less than k. Why is 1 less than k? Because k is your 2. So it goes to your case 3. Again you have to look at p. P is 1. 1 is greater than 0. So you are satisfying case 3.1. So what is 3.1? Your 3.1 is, it is simply of the order n raised power k log n raised power p. Okay. So what is your k? Your k is 2. So it is n square log of, what is p? P is 1. So it is n square log n. Fine. Now we'll see a last example for this Master's theorem. So if we have 4t n by 2 plus n cube, we have a recurrence of this form. So we can see here a is equal to 4, fine, and your b is equal to 2, okay, and your f of n is equal to n cube log of n raised power 0. Why? Because we don't have any log term there, so we can say log raised power 0. So looking at this, we can say your k is equal to 3 and your p is equal to 0. Fine. Again, we have to start from log a to the base b. So log a is log 4 to the base 2, it is 2. So it is equal to 2. Now we have to compare it with k. K is 3. Okay. So means it is less than k. So if it is less than k, we have to go to case 3. Now in case 3, we have to see the value of p. Now p is equal to 0. So we are now focusing on case 3.2 when p will be less than or equal to 0. So case 3.2, t of n will be of the order theta n raised power k here, case 3.2. And we can simply take it as theta, what is k? 3, so it is n cube. So implies your this recurrence is of the order that is theta n cube. So we saw Master's method in today's lecture, And we saw master's method for two different functions. One was decreasing function and another was the dividing function. For decreasing function, it was pretty easy. There were only two cases. But for dividing function, you saw that if we see in total, there are 6 cases. That is, case 1 is there. For case 2, we are having 3 subcases, and for case 3, we are having 2 subcases. So in total, we are having 6 cases. So what you have to do is that you have to simply check log a to the base b and k, and depending on that, you can calculate your running time. That is, you can calculate the time complexity of your recurrence. So you saw that this method is comparatively, it's very easy than your substitution, iteration or recursion tree methods, but you have to memorize these cases. There is no shortcut other than memorizing these cases. So I hope that you understood today's lecture, and that concludes our solution of recurrences. Thank you.